Hello, everyone. It is a pleasure to be here to represent both NASA and USRA in our annual site report at Qubits. I will spend a minute or two to discuss who we are, and then I will provide a report on the work in the last year or so. And I finally will conclude with a presentation of some current programs and opportunities. Our relationship with quantum annealing and the DWAM machines starts in 2012, when NASA Ames Research Centers, the University Space Research Association, or USRA, and Google decide to enter an agreement to operate a DWAM machine on site at NASA. And since then, we have not only installed the machine and managed its operation on premises, but we have upgraded it twice, and we're currently using the D-Wave 2000Q machine. The same year, 2012, the quantum group at NASA, the Quantum AI Lab, or QuAIL, was founded, and it has followed the evolution of the technology produced by D-Wave since the Vesuvius chip. And it also had access to a special mode of operation of the machine where we were allowed to run physics experiments, such as changing the temperature of the machine. So we believe that QuAIL is an advanced user by now, and the focus of the group is to use the machine not for using productions for applications in the near term, but it is to understand the power of quantum annealing for the design of exploitation of quantum annealers in the future computing systems. And we did publish over the years multiple reviews summarizing the perspective of QuAIL on applied quantum computing in the regime where machines are noisy. And I invite you to take a look. In those reviews, we put quantum annealing in the context of a larger field of quantum information processing sciences. And if any of you is in US government circles, you might also have had a look at the white paper that we wrote recently. And the findings of these white papers I gladly summarize here. First finding is that we believe that quantum annealers are and will be in the near term essentially the only devices where we can experimentally test quantum computation over hundreds of logical variables. And in the short term, they will maintain an edge in terms of end-to-end performance with respect to gate model quantum computers, especially for AI applications. And we also believe that there is a very interesting case in terms of workforce development for quantum computing. And also, we believe that the quantum annealers are scientifically interesting and impressive engineering achievements, since they implement many-body dynamics, which is very difficult to simulate. And but still, it's to a large extent under control. And finally, we could touch firsthand how research in quantum annealing is impacting research in other domains, both of classical computer science as well for implementations of digital gate model computers. So we can see how all these points emerge from NASA QuAIL research efforts in the last year or so, which is articulated in 4 main themes, and that I will now briefly review, as well as from USRA experience in workforce development and in engagement of the applied computing ecosystems that I will also review in the next few minutes. So let me start by reviewing a bit recent works that we published, that QuAIL published in the domain of benchmarking. In particular, shout out to a software suite developed in collaboration with Texas A&M University and our Salvatore Mandra, where we published in the context of the NASA Unified Framework for Optimization, a set of methods that are useful to generate hard Ising problems of different structure with known but non-trivial ground state solutions from the start. And this is important in order to be able to generate metrics, to evaluate metrics such as time to solution and others. And the software is open source and downloadable at this GitHub link here. In terms of embedding, the compilation procedure of the DWAM machine, I'll spend a minute to advertise 3 works. The first one, in collaboration with Carnegie Mellon University, is a numerical complete method based on mixed integer linear programming. and also presents a heuristic method based on logic-based Bender's decomposition technique, with the objective to improve upon the algorithm by Kai et al., which is used in the Ocean SDK, as well as the Find Embedding library released by D-Wave. And we found that for problems that are borderline in terms of embeddability, which are represented by the large triangles in the plot, both our new methods still find an embedding where the D-Wave heuristics fail. So we could use this approach when find embedding fails to score more wins, essentially. In other work led by our Jeffrey Marshall, we studied the problem of sampling the statistics of a classical logical Ising model through an embedded one. And we found that thermal sampling of the logical model is not possible through embedding in an efficient way, at least for classical Hamiltonians. And we have a theory which has been verified numerically on what is the distribution that is generated by thermal sampling of an embedded spin system. And we also demonstrated that this distribution cannot be fixed by majority voting, nor by any other post-processing techniques, although the paper provides indications on how to make things better. And still, this result is not discouraging in terms of machine learning applications, since they do not require perfect sampling necessarily. A third work develops a theory of quantum embedding using a 1D disorder system that can be solved analytically exactly. And this model, in this model, it was shown that the minimum gap, when it is generated by the Griffiths phase, which is a common spin glass effect, then a judicious parameter setting procedure of the embedding chains, which is dependent on the couplings of the logical problem, could open the gap and actually increase the performance with respect to the logical problem and the unembedded model. And so we have studied the optimal time to solutions of problems up to 1,000 variables, and we saw that this TTS doesn't grow exponentially, but quadratically instead, if the correct embedding procedure is done. So for future coherent annealers that want to operate in the adiabatic regime, this is good news and a very good strategy to explore further. Let's look at applications now. Yesterday, Zoe Gonzalez-Izquierdo presented some NASA work related to optimization of the degree-bounded minimum spanning tree problem, which was applied to the peer-to-peer network of multiple drones. And in that work, she showed how performance was investigated by an ingenious use of the pause feature of the D-Wave 2000Q. So since this was reviewed yesterday, I decided to spend a minute more on mentioning the work, which is the latest of a series where we have investigated the recall and representation power of quantum-assisted variational autoencoders. And this is a work led by our Walter Vinci. In the latest paper, it was investigated the performance of a quantum-restricted Boltzmann machine, which was implemented on D-Wave to assist the training of an autoencoder, which was tasked to detect similarity between time series representing daily variations of satellite measurements over pieces of land across the Earth. The database that NASA has is super large, it's petabytes, and the proof of concept that has been tested for training this autoencoder is over 45 million points, which we believe might be unprecedented for quantum machine learning. And what Walter discovered in this work is that the training performance to detect similarities of a classically restricted Boltzmann machine with a latent space of 64 bits is matched or even slightly outperformed by a quantum Boltzmann machine on D-Wave. And that machine uses only 32 logical spins instead of 64. And moreover, by simulating the Monte Carlo dynamics of the D-Wave machine, it was shown that under certain conditions, the training performance could be further increased if it was possible to sample at a finite transverse field, which is not possible currently on the D-Wave machines, but this is a good insight for future designs of annealers. Additional work I should mention is an ongoing collaboration with Princeton University in the design of systems that could decode wireless signals faster than what is used today for future 6G networks, I would say. In those works, we focus a lot on practical engineering considerations on what needs to happen for real-world production system to be deployed, which I think is something that as a community we should care about a bit as the technology progresses and becomes closer to useful beyond research environments. Finally, a quick review of a few works that we recently published where we look at theoretical aspects of quantum annealing. Initially in collaboration with Google and more recently independently, some QuaIL efforts are led by Gianni Mossi, which are looking at the power of resonant tunneling as a quantum effect to explore structured optimization landscapes. In particular, there are results of proven speed up for the detection of configurations of similar energy once starting from a configuration of the same energy, and this can be related to the recently introduced reverse annealing technique in the D-Wave machine. In other work, in collaboration with the University of New Mexico, we're looking at the thermalization properties of the D-Wave machine, and we try to understand how to exploit the power of pausing the anneal to increase the performance. And in that work, they were able to craft a numerical model which fits most of the observations. So very nice. And finally, a very active and very promising research direction that we're following as a team is to understand how analog quantum annealing relates to gate model quantum optimization algorithms. In particular, there is a compelling connection between the real-time continuous dynamics of quantum annealing in the region where the transverse field is of the same order of magnitudes of energy of the Ising couplings, which is where the magic happens, and the bang-bang protocol of the quantum approximate optimization algorithm, or QAOA. So the annealing time could be related to the parameters of QAOA and vice versa. And this is interesting since we know that D-Wave will be increasing control and universality of their machines, and that gate model computing, which is currently behind in terms of applications, can learn a lot from quantum annealing. So after discussing research that we perform, let me switch to an opportunity to work with us and to use the D-Wave machine hosted at NASA Ames. About a month ago, we announced a new partnership between USRA, D-Wave, and Standard Chartered Bank, which is a leading financial institution, to advance the state-of-art of quantum annealing applications. And as a result of this partnership, we launched earlier this month a competition to submit proposals, which is open now, to use the D-Wave machine free of charge for academic research. This is not the first time we do this. Over the last 5 years, more than 20 institutions gained access to the machine and published more than 30 papers, and some of these institutions are now regular collaborators of us, and they were recipients of grants from the government programs. And together with USRA, we worked on physics or NASA-related applications. So this is the case, for example, of Princeton University or Carnegie Mellon universities that I previously mentioned. And our partners at Standard Chartered are also eager to collaborate on machine learning and optimization applications of relevance for finance. So if you're interested in applying, the competition is open and can provide you access to machine as soon as October. So now only US universities are eligible. However, we have an interesting sponsoring program for private entities that want to invest in quantum annealing, and they are interested in machine time on LEAP. And they want to collaborate with USRA or NASA. So do not hesitate to reach out to me about this. One of the benefits of working with us is access to our trainings, which are specifically targeted to professionals of different disciplines and those that want to learn how to use quantum computing devices and design algorithms for applied work. So in particular, I'd like to showcase the work that USRA has done in collaboration with the Air Force Institute of Technology. for a course of quantum computing for the Air Force. And also I would like to showcase the quantum integer programming PhD course at Carnegie Mellon University, which is co-taught by me and CMU professors. And their students learn how to do a project to be solved with quantum annealing and other Ising machines. And some of this course material is available online to everyone, and some other is only available to sponsors. Another important program that we have is our Feynman Quantum Academy internship call, where 10 to 20 graduate students every year get to work with NASA on applied, theoretical, and other quantum computing related projects. So this year I could count about 8 projects that relate to quantum annealing, and applications are open all year round. So I encourage you to spread the word. Beyond the student experience and the training, this is also a great opportunity of collaboration with us. So actually, many of the papers that I showcased earlier are co-authored by these young researchers, and so we really target to turbocharge the career of these students by mentoring them towards producing good publications. Finally, let me invite all of you to subscribe to our NISC Computing newsletter. And this is a very different newsletter than those out there. What we provide is essentially an archive digest of all the preprints that have a contribution to the search of quantum advantage. It is a monthly email, so it's not very spammy. And there we categorize about 50 papers a month. And one of the category is experimental quantum annealing. And there we have about 4 papers a month that you should read if you want to know everything that is going on related to the research made with the Dewey machine. And also the category on in algorithms on optimization and machine learning are also quite related to quantum annealing. So we believe that with this tool, we are providing an incredible resource for keeping up to speed with quantum computing applied research. So, and you can also browse all the papers that we indexed over the last year and a half on our website. So this concludes my site report. Please allow me a moment to recognize that the work at NASA and USRA would not be possible without the funding provided by our government and private sponsors. In particular, the Air Force Research Lab, both for science and workforce development, together with NISTEC, DARPA to advance the state-of-art in quantum annealing, NASA to investigate space, aeronautics, and AI applications, Standard Chartered to push forward optimization and machine learning, and the National Science Foundation that has awarded USRA research grants, both for analog computing and for wireless applications with Princeton universities. And with this, I conclude. These are my contacts as well as the contacts of the government representative for NASA and the technical lead of QuaIL. Thank you for the attention.